Okay, welcome to Lecture 5. This week, this lecture is going to be split up into two parts. So we're going to talk about convolutional neural networks and the kind of underpinning theory of them in this particular lecture. And then we'll also talk this week about some frameworks, and we'll kind of work through the anatomy of setting up a, the training of a neural network in the context of a framework such as PyTorch, and sort of discuss that. And then hopefully with all of these pieces, now we can start to kind of move into other things in the coming lectures, such as recurrent neural networks and how to use them. We're starting to apply these kind of underlying concepts to different kinds of problems, tasks, especially in the context of some of the games and simulation type of applications. And we'll actually see some of that in this lecture as well, which I'm pretty excited about. So to kind of recap and review what we've talked about thus far, we've discussed the sort of machine learning problem, right, where we have a system, a function of some kind that we're trying to learn. We're trying to approximate this very, very complicated function by way of a class of different function approximators which learn to improve based on experience or data, either online, offline, or in whatever combination, shape, or form. And so we've discussed already the multi-layer perceptron, or the fully connected layer, right? And in the context of a linear combination of features, then be applied through a nonlinearity, and you kind of rinse and repeat per an objective function. And using this kind of model, you can do a lot of very, very interesting things. But there's some limitations with this, both in terms of just overall compute capacity, like for example, if I have a fully connected layer of 1,000 hidden nodes, hidden neurons, and 1,000 input parameters, input features, and then additional, every single one of those layers is going to constitute a 1,000 by 1,000 matrix of weights. So essentially a million weights. And if you think about this in terms of a 32-bit computer architecture, right, for each one of those, say we're doing a 4-byte or say an 8-byte, floating point. Let's say 32 bytes, so 4 bytes, right? So 4 bytes. So for each layer we add to our network, we're going to have to deal in 4 megabytes of data, right? And that's both in terms of the computation, so we have to process 4 megabytes times the number of layers. We also have to deal with the actual memory, right? So we have to move that much data in and out of the GPU or whatever computational framework we're using. And there's a lot of problems with this. And keep in mind, 1,000 features, if you're thinking about, say, something like an image, is not very much, as we talked about, right? A 32 by 32 pixel image with 3 channels of color will actually be, I think, what is it, right, 2 to the power of 10. So that's like 512,000 times 3, which is 3,000. So in fact, so a 32 by 32 image with 3 channels is going to be approximately 3,000 input features. And so already we're talking about 12 megabytes per layer. And as you know, as you make bigger images, it goes up not by a factor of 2, but by a factor of 4, right? Because if we make something an image twice the resolution, we're actually multiplying the width and the height by 2, or the whole number of features by 4. And so you kind of have this really difficult problem. In other words, the fully connected layers are awesome to kind of fundamentally to think about, but there are limitations. So enter this new concept of convolutional neural networks, which we'll talk about today. But before I talk about how this can solve some of these problems, let's first talk a little bit about what convolution even is. So here we go. So what is convolution? From the more strict digital signal processing standpoint, a convolution is similar or can be thought of as sort of sliding a template or sliding this matrix, this H matrix as shown, or a vector as shown here. It can be a matrix as well, right? You can have 2D convolutions, and then this, sum here would actually be a bit of a different, you'd do it over both the y and both the vertical and the horizontal. And you can also have a number of dimensions, right? The only stipulation being that your H, tensor has to match the dimensions of your input tensor. So if you have a convolution, a 1D convolution, then you're convolving a 1D signal. If you're convolving a 3D signal, your kernel needs to be 3D. But let's think about the sort of 1D scenario here, which is kind of an easy one to visualize. So say you have a convolution vector of 1/3, 1/3, 1/3. And so what would be happening is you would take three consecutive values in x, multiplying each of those values component-wise by those values, and then summing them together. So it's almost like you're doing a dot product of the window of the vector that you're in, of the input vector, times the kernel. So it's almost like you're moving this kernel around across your input signal. Often, by the way, the convention is that this middle point, the center of your kernel, is where you're operating, and so you would apply, like, the middle is kind of like the center of the convolution, but mathematically it kind of doesn't matter. This is sort of the infinite form of the convolution, and so this actually covers both situations where you can even do things like having I in the past, which I won't get too deep into digital signal processing, but ultimately there are kind of ways to deal with what's called finite FIR filters, or finite impulse response filters, and also infinite impulse response filters, which allow you to do very complex and interesting things to your signal. But that's kind of beyond the scope of this class. For the purpose of what we're going to be doing, we're really looking at the finite case. We're only going to be dealing with signals that are in front of us, and we can always sort of predict what they are. So this example of 1/3, really what it's doing is if you can kind of see, it's calculating a runtime mean of our signal. And so if, say, you have a really spiky signal, as you can see here in the image, right, that's your x of n, and you pass this h over it, what you're doing is you're calculating the window of 3 average at any given point, and the result is going to be this kind of smooth curve, or smoother curve, right? And you can kind of see that the wider, by this kind of equation here, say the h value at a particular point in a vector is going to be equal to 1 over its length, right? The lengthier, the bigger of the window that we use, the smoother this curve is going to be. For example, if n is equal to the length of x, right, to the length of your input signal, that case we're simply calculating the average of the entire signal, and you're going to have a flat line. However, if n is equal to 1, all we're doing is we're multiplying the value of x by 1, and that's the value. And so you can see, as we take n, we go from the input signal to purely average. And the way that you calculate these values is actually quite dynamic. You can do very, very interesting things with this. This gets into DSP, of how to actually figure out what your what's called the transfer function result of a particular convolutional filter is. But you can, for our purposes, we never actually have to figure out what they are, because we're going to learn these parameters in the context of a neural network. But just to kind of talk a little bit about convolution in the 2D case, one really popular example are these class of filters called Sobel filters. And you can see their form here. So in this case, we're talking about a 2D convolution. And the way that we would apply this 2D convolutions, you can imagine taking this and applying it to your image and sort of sliding it in both x and y. And so you're kind of applying it, and we'll talk more about the mechanics of this. But in the case of a Sobel filter, we have two filters. We have one for x and one for y. And what you can see here is the left side of the filter is negative. the right side of the filter is positive, and the middle is 0. And what that means is that if you are in an image where the left side of this filter has a lower value than the higher side of the filter, that means we can detect that as a gradient. So these are actually detecting the rate of change of our filters and detecting areas of high frequency change. So you can see the Sobel filter applied to an image where essentially it results in an edge detector, because what we're doing is we're saying, oh, if there's a situation where on one side of the edge we have a different value than the other side, we're going to return a relatively high value for that point. But if I have, a very flat region where the entire area is the same values, these -2 and 1 and 2, these will cancel each other out. So if it's equal, this will cancel out this, and you'll get 0. But if it's unequal, we're just going to sort of amplify that difference. And so we do that both in the x and the y direction. So you can kind of see we can composite these. If the convolution of each of these is different than, like, say you add these filters together, you're not going to get the same result, as you can kind of imagine. We're not going to go too deep into the mathematical principled approach to this stuff, but it's maybe an exercise for you guys to try at home. And one thing I wanted to kind of point out, given that this is in the context of games and simulation, there is a very, very popular anti-aliasing technique that uses heavy use of Sobel filters called fast approximate anti-aliasing. And what this does is it will take your image and it will run a Sobel filter over it to kind of come up. You can see this is the bottom right image. This is from the FXAA paper, which is a great read if it's interesting. And what it does is it calculates the areas of high frequency in your image. And then in those areas, you don't do this approximate anti-aliasing. And everywhere else, you apply a Gaussian blur. And that sort of approximates this thing. And so you can use this edge detector as a kind of mask for your Gaussian blur. And the interpolation, as you can see, this is a continuous interpolation. You don't get these really hard edges. You have this sort of, incremental thing. So if you're doing this properly, right, areas of high frequency information get this sort of interpolated blur applied to it, and it's quite an effective technique. And there's a bit more nuance than what I'm explaining here in the actual FXAA process, but in terms of actually implementing this, which I've implemented this particular algorithm, it actually is quite eloquent and uses this technique. So this is just one great example. So before we move on, let's sort of think, okay, how do we connect this idea of convolution to neural networks? This seems really valuable, right? Because if you even think about here, it kind of already looks like this linear combination. We've already seen this idea of the dot product, and when n is essentially the length of our input vector, we are essentially just doing a multi-layer perceptron. So there is this sort of almost linear connect between convolution and this linear combination of features. But what are we? How would we apply this? And so let's think about that a little bit. And so let's recall the perceptron, right? And the perceptron, again, is a linear combination of weighted features. And the way we do this is almost just like what we saw with the convolution, except we don't have this concept of a sliding window. But what if we did that, right? What if we did apply this concept of a sliding window? So imagine your input vector being a piece of tape, right? And now we essentially take our perceptron and calculate the value at any given point. And then we just sort of sum this together. Why would we do that? Why would this be valuable? Apart from obviously having fewer features, so we are getting fewer weights than the alternative, right? In this case, we don't need to have a weight for every single feature vector, for every feature of the input vector, but we do need to sort of understand, like, why would we do this, right? In this case, what we're going to get is we're going to get a different value for the perceptron at any given point. So why is this good, and how do we deal with those different values? And so given that this sort of represents a neuron, the idea here, by the way, would be that we slide this across and we get a value for every single point, and then we would sum that together. We would get a final value for that. But why would we do this? So let's kind of switch our perspective a little bit and think about this in the context of a 2D image, right? Now, say we have an image of a ball, and the ball is in the bottom left corner of the image, and then we have an equivalent ball, but it's in the top right corner of the image. If we plug that into our multi-layer, into our perceptron, into this linear combination, you can see that unrolling this image, if we take it like pixel by pixel and slap it onto a particular feature vector, from the perspective of the network, this is a very different input vector than that, right? And so we're going to have to learn a shift invariant function, as it's called, which is going to be very difficult for our features to deal with. We're essentially going to have to almost have a layer per this kind of thing, where we have to sort of somehow determine that these features have moved over here, and then generalize that in some way, and then push it through the network to get to a point where we can generalize that sufficiently well. And as we discussed, right, for every layer that's fully connected like this, there are a ton of parameters. And that means that very quickly this becomes sort of computationally infeasible. Although there's a very good paper, by the way, that sort of talks about, can we teach a fully connected layer to behave like a convolutional layer? And the answer is yes, but you do have to do a lot of heavy lifting and a lot of very key manipulation to these linear layers to ensure that they become shift invariant, as it's called. So at a high level, the intuition here is, and with a linear combination, sort of naively, when we move a image, we kind of change the content of the image, but we're not changing what it means, meaning we're moving a ball from one point to another, right? Imagine the situation of a cat, right? A cat may look very different in many different pictures, but still be a cat. How do we deal with that scenario in a way that is shift invariant, that kind of deals with more spatial or sort of contextual or frequency-based aspects of our network? And so you can already hear that there are some benefits that we can use from the convolutional neural network. As you saw in this image, as we can see, convolutions are particularly well suited for detecting particular frequencies and particular changes in signal in a very specific way. Like, for example, here, more explicitly, this is just an example of a filter, but what you're doing in the context of an averager, you're doing a low-pass filter, and so you're taking a signal and you're extracting from it its low-pass components. And then in the similar way here, in the Sobel filter, you're doing the opposite. You're taking an image and you are extracting from it the high-frequency components. And so in this way, a convolution could basically be used in the context of an image like this, where you want to understand the underlying content of the image regardless of how it's sort of shifted and manipulated. So let me jump to this next slide just to kind of explain it, then I'll go back to this condition number, which is a very interesting kind of line of thought that I want to share with you all. But if you think about this idea, right, instead of dealing in the entire image, what we're going to do is we're going to say, okay, we're going to define a particular convolution filter that is a height and a width, like a particular kernel, and we're going to slide that over the entire image. And as you can see, because we're defining this little window, right, the window of the object here is going on this left image is going to result in the same feature vector, because ultimately a convolution just results in this linear combination. It's just over a window of our input signal. So it's not the whole thing, but it's just sort of spatially sampling a particular portion of our input. And then equivalently here, when the object has been moved to a different portion of the image, right, that window, we still hit this, I know I'm kind of like hand waving here because the mechanics of this doesn't guarantee that we're going to get the exact same window on the exact same object in the exact same way, but, bear with me that in theory, given this window and this window, the output feature vector from the perspective of our network, from our sort of perceptron, from our neuron. We actually should start thinking about each kernel filter as its own neuron, right? So this particular neuron sees, maybe is trained to detect this particular pattern, and so it can find this pattern here, but it can also find this pattern here. And it's equivalent because as far as the input features to that neuron, we see the same thing. And so that's very, very different than here, where here we would have to learn the same feature vectors down in this area of activation as we would have to see in the top area of activation. Then how do you deal with a layer that basically has to have, this very, very complex thing? You have to basically layer them like string cheese, many, many different layers to detect all the different potential permutations of our input values. So another way to think about this is in terms of what's called the condition number. And the condition number essentially represents the change of a particular function in its output with respect to the underlying change in its input. And so this is the equation as the limit of the error as you go and you create the perturbation, you make the perturbation smaller and smaller per the supremum of the delta x in that sort of epsilon. So imagine x being a multi feature vector, and so you have to kind of choose the set of values that still are within the epsilon in the error. So if we have a very complex function, it's kind of like a nomenclature. Just say we have to choose the sort of least upper bound of our changes in x given this particular epsilon that's going to 0. And so we're kind of, it's a stupid nomenclature, but it works. The point is, as we take the limit of our manipulation in f, what is the respective delta in x? What is the respective delta in f? And so this is from a really good paper called Neural Networks in Adversarial Setting and Ill-Conditioned Weight Space, which, by the way, this is a different subject to talk about, just how these neural networks, everybody talks about them as being really complex nonlinear functions, but that's not really true in terms of how they behave with respect to input, because this condition number, even for a really complex linear combination or a convolutional neural network, ends up being a relatively linear thing. And so by moving it a little bit, you get a respective change in the kind of behavior of the network. And this is if you're operating on the input. But one thing to kind of note here is that the ultimate, the convolution here, the condition number is going to be defined as less than this upper bound of k, of this condition number of the weight matrix. And the weight matrix is going to be defined up here as the sort of norm multiplied by the norm of the inverse. And so you can see that when, this kind of is such a stupid thing, it's such a indirect way to explain that when you change the matrix a little bit, everything changes too, by an equivalent sort of factor, which is defined up here. And one thing I think that you can note is that when you do this for a linear combination, such as this right here, ax plus delta x equals b plus delta b, you're going to essentially, for every perturbation in x, your entire output's going to be shifted by that aspect of the weight matrix. So that's one thing that's really kind of valuable in terms of the convolutional neural network, where this still applies, but that applies within a window of the input. And so you're kind of, the amount of perturbation of the output per the input is windowed and reduced by the fact that you would have to shift the entire image before you can actually get here. But by the way, you can still do this, and this paper doesn't talk about how convolutional neural networks are better than linear networks at this, because they're not actually at all. They're just, the effect is less. And the reason that this is valuable, the reason this is good, is because these are shift invariant properties, meaning if I move something from here to here in a convolutional neural network, it won't largely affect its behavior, because these operations are limited to what's called the receptive field of a particular neuron, which is defined by its size, which we'll talk about in a little bit. But with that said, like there are plenty. This paper actually discusses a current sort of limitation and the weakness of convolutional neural networks or neural networks in general, where their behavior is still linear. Their classification behavior. There are these vectors. There are these perturbations that you can apply to images that move them linearly in the sort of space that they're operating in, such as classification, for example. If anybody's interested in this, please ask me in the Discord. There are papers on the subject where you basically can take an image of a panda, add to it some kind of perturbation, meaning a noisy kind of input, and then you pass it through an image classification network, and the output will then give you zebra. There's plenty of examples of this, and this is actually trying to quantify that in terms of this condition number, because you can do this in either way. But the point that I'm trying to make here is for you to think about is in terms of the different condition number of a linear model versus a convolutional model, because of this really, really attractive property that convolutional neural networks are shift invariant. So just to kind of, again, visualize the shift in variance, you basically can take this image, right, move a component of it, and largely we can expect the same output. The other thing that kind of is often sort of waved, the flag is waved on convolutional neural networks, is this idea of weight sharing. And we kind of already talked about this, but to visualize it, I like this image here, which kind of demonstrates, right, for a particular neuron. A neuron is defined now not as a hidden unit in a particular multi-layer perceptron or in a fully connected layer, but rather as this convolutional filter, and we may have many filters. And so, for example, in this case, we have a kernel of 3x3, so we have a 3x3 convolution like we saw with the Sobel filter going through the entire images, and we have a number of them. We actually, in this case, looks like we have 32. So we take this 28 pixel image, and then we run 32 different 3x3 kernels through it. And keep in mind the mechanics, and we'll talk about the mechanics in the next slide. The mechanics of a convolution is we're actually going to take our input channels and sort of sum them together. We're going to squish them down for each neuron and for each filter. And so what we can then do is we just have these weights that are shared across all of the input images for that particular neuron, meaning the weight for the top left part of the image is the same weight as the bottom right of the image. And so in that sense, we're sharing weights across the entire span of the input, and as compared to, say, a fully connected layer, we have very much fewer parameters. Right? For every neuron, we would have, in this case, 3x3, so 9 weights, and we would have still 32 neurons. So we would have 9 weights times 32, but that's a lot less than 28 times 28 times the number of hidden units. And so no matter what we're talking about well fewer weights per neuron than we would in the fully connected layer. And actually, when you look at a lot of these networks, the biggest, the heaviest, the largest amount of weights are generally in the final fully connected layers at the end of the network. The reason that people do this is because they'll terminate with these sort of fully connected layers and then apply our softmax, our loss function, be it Euclidean or one versus all or whatever you want to do on these fully connected layers. And so the way this works, by the way, is we take our input tensor and we kind of unroll it. So now for every for this final stage, we have 64 by 7 by 7, for example, in this image. And so that's the number of parameters, which then are treated as a unrolled, flattened feature vector that then goes in here. And as you can see, right, this next input stage has 3,000, input 3,000 hidden units, because one per 3,000 parameters per hidden unit. It only has 128 units. Sorry. But for each unit has 3,000 parameters, and so if you compare this value to any of these, it's well above, right? It's a huge number as compared. So the generally the end of the networks are just look like these multi-layer perceptrons to then behave and do classification and to kind of combine these things into what's called a feature representation of some kind per the more spatial thing. We can talk a lot about this. I'm not going to talk too much about how these networks look and in operation too much. We'll talk a little bit about it during this lecture as well. So the one kind of downside you might be thinking is like, well, how do we calculate the gradient? The only thing that's different here is now, instead of dealing with the gradient per parameter, a particular value may contribute to many gradients, right? So because you're taking these weights and sliding them over your entire image, right? Given that this is still a dot product, right? So the gradient of this operation is just going to be, if you take the gradient of a weight, it's going to be just the parameters that contribute to it. And that's the only thing we kind of have to take into consideration. And it's kind of convenient because out of this, and I'm not going to do the mathematical breakdown of this, and there's a nice blog post I linked down here, so if you're interested, wrong way, you can see it. You can click that, it's in the PDF. But it kind of breaks down that, right at each stage per backpropagation we talked about last time, we get these sort of output gradients that we're then going to kind of backpropagate. And so out of this sort of mathematical, if you do the mathematical kind of breakdown of this, what we're really doing is just we're doing a convolution of the output gradients against our input data. So we're just convolving the gradient of each neuron, or of each parameter in our neuron by the input values, by the input features, which kind of makes sense, right? Because for every value, we want to have all of the different parameters that contributed to that, and then as a result of this, we're just going to get a sum of that because we're going to convolve it, and then the output of that is going to be a sum at each point, and then we can then backpropagate those gradients to where they came from, if that makes any sense. So yeah, pretty convenient actually. So fun stuff. It's pretty clean. So let's talk a little bit about the anatomy of a convolutional neuron. And then the convolutional neuron, again, is one filter in this sort of stack of filters. And so for a particular layer, you may have three 3x3 filters, as shown here. And so what's happening here is what we do is we take these values and then we slide them over our input features, and you can see this is, these are multiple channels. And the reason we have multiple channels, we actually sum them across. And so in this case, in this case, we actually have two filters, and we have to have three different channels for the filter because the input channels is 3. And then what we do is then we sum them together. As you can see, this really nice image sort of shows how the three filters, how a filter then gets convolved, and then which ultimate value it contributes to. So I can't like pause this. I wish I could, but I recommend sort of sitting here and just staring at it and kind of understanding fundamentally what's going on. But in this case, right, you have your first filter. All of these are 3x3. This is the kernel. You would then take these values, multiply them by the respective window, and then you would add all of them, and then you would do the same for each one of these, each channel of the filter, and then you would add them together, essentially. And then that's the resulting value. And you can kind of do this for yourself if you're interested. But the underlying sort of anatomy of the neuron is defined by a particular neuron, a particular layer is going to be defined by a couple of different parameters. For example, the kernel size. The kernel is usually square, as you can see here. 3x3 is a pretty common one. You see 5x5, 7x7. Often you want to do odd because the number sort of adds up a little bit easier in terms of what the resulting convolution means. But you can do any number. You can also do non-square convolutions. That's kind of up to you. The stride then determines by how much do we then shift our convolutional operations. You can see here on the right, the stride is actually it looks like 2 because we start at 0, but then the next one we go to 1. So we actually go from the first column, and then the next time we go to the second column. And when we jump to the next row, we do so by 2. And so the stride determines sort of at what spacing do we then apply this convolution. So a stride of 1 would just mean we do the convolution, we move over by 1, and so on and so forth until we get to the end. You can have a kernel of a variety of different values. Padding, then, you can kind of see here the output volume is not going to be the same dimension as the input, right? In this case, our output's going to be only 3 by 3, whereas our input was only 7 by 7. And by the way, our output, by the way, you can see is 2, is 3 by 3 by 2. And the reason it's 2 is because we've run 2 filters on it. And as I mentioned, the filter essentially squashes everything down into a particular value per filter. It's almost like one neuron, so you're outputting a particular neuron. And so the way this works is sometimes you would want to output the same size, or you want to output a particular kind of size. And padding allows you to do this because, as you can see, the convolution operation for any non-1 size kernel is going to reduce the size of our input, or the output's going to be smaller. The equation is actually down here. And so if we want to make sure that our output dimension is equal to our input dimension, then we have to ensure that this particular equation down here at the bottom is equal to the input dimension. And the padding kind of helps us do that, right? Because in the context of an output dimension, it's going to be equal to the input dimension minus the kernel, right? Because you can imagine when we get to the end of the kernel, we can't go any further, and so that amount we can't use that space, and then we can add space to our image by padding, by 0 padding. So now we can widen it, and so we can compensate for our kernel size by basically providing a padding of kernel divided by 2, but the size of the kernel divided by 2. And then the whole thing is divided by the stride, so if you want to have a non-1 stride in this case, you have to again manipulate this whole equation to kind of get to the correct output dimension. And then finally, a particular convolutional neural network layer will be defined by the number of filters, and this will essentially tell you how many output channels you're going to have. Like in this case, we have 2 filters running over these inputs, and then now you have a 3 by 3 by 2 thing. And the reason it's 3 by 3 here is you can see we have a padding of 1 with a stride of 2, and the input is 7. So let's go through here, right? 7 minus 3 is 4, plus 2, because 1 padding is, the 7 minus 3 is 4, plus 2 is 6, divided by a stride of 2, which is 3 plus 1, shouldn't be 4. One moment, I'm going to pause and make sure I know what I'm talking about. Sorry, I wasn't reading. I was reading the number and I wasn't thinking. The actual size here, the actual width, is 5, right? The input volume is actually 5 by 5, not 7 by 7. 7 by 7 is after the padding. So we have input dimension of 5 minus a kernel dimension of 3, which is equivalent to 2. Then we add a padding of 1, so we add 2. So 5 minus 3 is 2, plus 1 divided by a stride of 2. And so now we have 1.5, and then we add 1, and now we have 2.5. Wait, 5 minus 3, 2, plus 2 is 4. I'm sorry, I'm an idiot. So 4 divided by stride of 2 is 2, plus 1 is 3. Okay, yes, we know math, ish. So yeah, this is how you kind of work through it. Keep in mind, I think I may have misrepresented one thing about convolutional neural networks, which is this bias term. I don't talk about this too much, but you don't always have to have a bias term. And in the context of this, the bias term just gets added at the end. And so you can see for every value, the bias just gets added at the end for every particular value that you're calculating. So yeah, it's kind of a very straightforward kind of idea. In practice, gets a little bit sticky, but pretty straightforward to kind of understand as well. One thing that you'll often see in these networks, in fact, in this network, you've seen it too, right? There's max pooling, this idea that ultimately just sort of, you see here, we have a 32 by 14 by 14, and then now we have a 64 by 14 by 14, and now we have a 64 by 7 by 7. And what this max pooling does, it goes from the 64 layer, the 64 filters of 14 by 14, this input, this activation layer, to this. It just divides your dimensions by half. And sometimes you just have this situation where you want to sort of incrementally shrink the size of your tensor in some way. And pooling layers is one way to do this, because and the reason you'd want to do this, right, is to, again, deal with parameter count. So by the time that you get to your output, if you have the same number of features as you did on your input plus all of these neurons, you now kind of have defeated the purpose of using convolutional neural network layers to reduce the parameter count in your model, because now you have even more models. Now you just have, 32 of your input image feature sizes, and so that kind of backfired. And so often you'll see this sort of almost like funnel type of architecture in convolutional neural networks, where it goes from a high resolution to smaller and smaller but wider. So you have a smaller resolution but more channels, and further until at the end you only have these fully connected layers. And to accomplish this, you can do this with convolution, as you saw here, right? We're able to apply our convolutions in a particular way such that our output volume is smaller than our input volume. But maybe that's not necessarily what you want. What you want is sort of to say, I want to treat regions and areas, and I want to then sort of route information in a particular way. And pooling layers allow you to do this, either by treating areas of your tensor, your input activations, in an average way, or by only dealing with the highest activation of a particular area. So the two kind of common pooling layers that you'll see often are max pooling. And in a max pooling scenario, and pooling layers are often just defined by a stride. They don't have any weights. You're not actually applying anything to the data. You're just sort of looking at your input, and then you're striding the pooling operation on that input. And so, for example, when you have a stride of 2 in a max pooling, like this is the example shown here, you would be given, say, a 4x4 input matrix. And to apply the max pool operation here, we would look at each 2x2 section and then find the maximum value. So maximum pool would then say, okay, in this top left window, the maximum value is 6, so we put the 6 here. In the green, it's 8, so we put the 8 there. In the yellow, it's 3, and in the blue, it's 4. And so you can see the output of a max pool 2x2 with a stride of 2 in this case is essentially just the maximum values in each given window. You can also do this with average pooling, and so average pooling would then take all of these values and then apply that averaging convolution we talked about in the beginning, or just takes the average. Now, one thing that's kind of notable here is that there are no learned parameters. So max pooling can't turn into average pooling. If that's something that you're trying to do, you need to use just a convolutional stage, which is what you can do. You can say, hey, I want to do a convolutional stage with a stride of 2 on this thing, and you can kind of calculate what the stride and the kernel sizes need to be for the equivalent max pool or average pool operation, and then your network is free to learn this operation if you were to want that. But in some cases, we don't want to learn it. We don't want more parameters. We just know we want to reduce the size of our image by a particular factor, and so this we can use. A thing about implementation here, right, in terms of this, the gradient of these layers is almost like a kind of flow. Right, so at this point now, when we look at the network, our gradient is only going to be applied to from 6 back, right? So when we get our output gradient from the preceding stage, right? Then we get this output gradient only applying to this value of 6, and so we then only apply that output gradient to this 6, and the rest of these values would no longer get output gradient. The flow would then get stopped, and in a way, would no longer, would only flow into whatever neurons that previously contributed to that value of 6. So in a way, these max pooling layers are kind of like gradient routers. We can kind of say, oh, this neuron contributed to this output, and the output contributed to the loss. And so in that sense, we only want to deal with that. And in a way, that can be a way to optimize the training of your network for a variety of different kinds of inputs. Keep in mind, this is kind of oversimplified because the input to a particular neuron, it's not so simple when you put these things together. Like these values are not going to get any output gradients. You're not completely stymieing the flow of gradient flow, but it's something that we can discuss more if that's interesting. Alternatively, the average pooling operation kind of then takes the 6 had an output gradient that it's getting during the backpropagation phase, right? So now what we're going to do is say 6 is the average. I know it's not, but say this value is the average of all of these. We would then take that gradient flow, that output, and then average it across in the backward direction. And so then all of these neurons would get an equivalent gradient flow. And so in a way, that's the average pooling. And unlike a gradient flow, a gradient router is almost like a gradient averager as well. So it kind of, you have to think about the dynamics of these layers, the dynamics of these operations, not just in the forward pass direction, but also in the backwards pass. Because keep in mind, the dynamics of your network is going to very much affect its ease of training, and as a result, its ability to perform in a given task in a given domain with a given data set. And so that's something to really kind of think about a lot. On that subject, so I'm going to talk about a couple of, really kind of interesting aspects that usually we don't talk about, like in the classes I've taken, don't get really discussed early on, but to me are very interesting. And I think given the context of this being a topics class and a seminar more so than a, really rigorous, like, hey, build a LSTM backprop for the 5th time, this is a great place to talk about it. And in terms of what you guys do for your projects or your homeworks, I would really encourage you all to sort of explore, because residuals, by the way, in particular, are super, like, in fact, both of these ideas that I'm going to be talking about in a second are super easy to implement. They're literally just add a thing to a thing at the right time. If you're using a framework. If you're not, then it's a different story. So residuals, we were just talking about this concept of gradient flow, but something to think about in these sort of very deep neural networks. Let's go back to this image here. You can see how the output may have a gradient that's particularly strong, right? Because we know the loss, and we know the gradient of the loss. We can calculate it directly in terms of these values, these logits that contribute to it. So I can determine the very, very strong gradient on this particular neuron, as we saw with just linear regression. In fact, linear regression, you can go all the way to the point where you can analytically solve for the exact value that would then change that weight to be perfect, or to the minimum, right? So the gradient at this stage, at this output, or the top layer, is very good. It's very large. It's going to have a large magnitude. But as we flow backwards, think about we're kind of chaining these gradient updates, right? And if the norm, if the average, kind of the norm of those weight updates is not going to be, if the averages, if the norm of the weights, because the weights get applied to each kind of incremental update, if that's not going to be equal to 1, then 2 things can happen. If it's greater than 1, the gradients explode. They start to get bigger and bigger and bigger as you go backwards, and can eventually just get so big that they make our numbers completely garbage. Because again, we're on a computer, and a computer can't deal with these massive numbers at a certain point. It's going to say, hey, this is beyond my ability to represent these as numbers. And also, it's important to be rooted in what this stuff runs on, because in theory it's maybe okay, but in reality, right, floating point precision is a real thing. As the number you're dealing with gets farther away from 0 in floating point numbers on a computer, your precision kind of goes to shit. as well. And that means that the dynamics of your training process, which is already a stochastic and kind of sampling-based process, starts to go in the toilet as well. So the exploding gradient problem is when your norms of these weights are beyond 1, and by the time you get to this sort of like first layer, your gradients are all over the place and are useless, and it's very, very difficult to train your network. There are other issues, by the way, that contribute to difficulty in training, which we'll talk about maybe later. Maybe we did already talk about it actually with batch norm and neuron saturation. But exploding gradients is one way. One way to avoid, by the way, exploding gradients. So exploding gradients is the easier one to deal with, but you can clip the gradient update. So you can just say, hey, I'm not going to update more than a certain amount, and that can help a little bit. But the more common case is the opposite, not the exploding gradient, but the vanishing gradient problem. So if our norm of our weights is less than 1, then what we're going to do is we're going to be kind of incrementally reducing our gradient update by exponentially by that norm. And that means that by the time we get to the beginning, our gradient is essentially 0. And that means that it's very, very difficult to train this network. And so this is kind of shown here, the gradient of a particular layer, of a particular layer, activation of a layer, the gradient of the loss in terms of a particular activation layer is equivalent to this product of the weights of a particular layer kind of getting up to that point, and also the and the gradient, kind of like the output gradients of that layer. So again, in other words, as we go backwards in time, backpropagate, our gradient update will kind of get smaller and smaller and smaller. And so you can actually see in the literature that networks sort of got to a particular size, like VGG 16, which we'll talk about in this lecture in a minute, got to 16 layers, but started to kind of struggle getting bigger and deeper. And there's a bunch of papers from that era talking about, trying to overcome this vanishing gradient and exploding gradient problem, but largely the vanishing gradients. Then this idea came around, residuals, or ResNets for short. And what's done here, and this is kind of like unintuitive in a way. So you have a layer. This is a convolutional neural network layer or whatever. It doesn't really matter what it is. And you then apply the nonlinearity past that layer. Then you pass it to another layer and then output it. And then to that output, you were then just adding the input value from that previous weight layer. And so the output then is, say, these two layers kind of result in a collective f of x. The output of that is now f of x plus x. And this is done kind of incrementally for the entire network. And what this does is it provides a direct flow for the gradient all the way back to any given layer. It's almost like kind of having this chain of the output network, of the output loss gradient being available to any particular point in the network. And so what this does is it changes the loss at a respective network from this product to a sum. And this resulted in significantly better ability to train very, very deep networks. In fact, the ResNets can be extremely deep. I think one of them is 152 layers. And the ResNets, in terms of a lot of the computer vision tasks like detection, classification, and so on, have really kind of become state of the art. But there are a number of different architectures, so I won't claim that ResNets are the best way anymore. But in terms of training very deep networks, the residuals are a very interesting way to approach this. There's another thing you should think about in terms of this, which is batch norm and layer norm. This has to do with how fast you can train a network in terms of the actual, activations of a network in terms of keeping them within a particular bound. And this also kind of applies to the same idea, where you're trying to ensure that each layer maintains a kind of statistical model of having a mean of 0 and a variance, a standard deviation of 1. And that way you're not too far away from where you're supposed to be, and you don't have to nudge the gradients too far. And this also has to do a lot with the sort of vanishing, well, it has to do more, I think, with the saturation problem in terms of sigmoid, but if you're using ReLU, it still kind of has to do with this ability to sort of train these things quickly, because your gradient isn't like these big numbers. They're kind of small and easy to work with. So residuals plus batch norms have really kind of become the sort of I think state of the art for especially computer vision models that deal in spatial information. So residuals are super cool and very, very easy to implement in terms of these. In fact, I think a lot of frameworks have residual blocks, but to implement a residual block, you literally just layer a couple of these different operations together, and then to the output you add your input. Another thing that's, I think, really interesting to talk about, and I'll move myself here because I'm covering the thing a little bit. Yeah. Here, I'll be in the image. Cool. So in some cases, you want to have the output of our networks output something that is not just a classification or a regression, right? In the context of classification, we get a bunch of outputs that tell us if this is a cat or not a cat. In the context of regression, we're talking about a value, continuous value. But in some cases, we want an image kind of like what I'm on top of here, which is this sort of, say I want to take a picture and I want to know what all the pixels in the picture represent. Now I can do a per pixel classification like we've talked about, which is kind of the way this is done, but also we can think about this, how do we do this purely convolutionally? Well, the issue then is the output, as we talked about, starts to kind of get smaller and smaller and smaller. And ultimately sort of terminates in these fully in these fully connected layers that then we use for classification or regression. But we can think about a different approach here, which starts with this idea of the transpose convolution. And so the convolution can be thought of very easily as a downsampling operation, as we saw in a lot of these slides, right? We're taking this input and we can very easily create an output volume that is smaller than our input. We can make an output volume that's bigger. However, in this context, we would have to basically zero pad the shit out of it, and so we would just have a zero padded output. So it doesn't really help us. We're still going to have a smaller volume that is, basically either the same size or a smaller size than our input volume, given that it's non-zero. So a transpose convolution is sort of a way for us to upsample, and it's the reason it's called a transpose convolution is if you look down here in the bottom right, if you think about a convolution as a matrix multiplication, the way you would do this is you would essentially stride these values the way that you're seeing here, x, y, x, y, x, y, x, and then you apply it to this vector multiplication, and now you get, with zero pad, and now you get this, and this is sort of the convolution in a 1D example. And the equivalent can be done in a different way, where if you instead transpose that matrix, and now you apply this without the zero padding is no longer part of it, as we mentioned, right? Because you don't need to deal with that. You get an output that is smaller, that is bigger. So in this case, we get an output that is smaller, right? Because then the one moment, let me kind of explain this a little bit better. Sorry, I totally butchered this explanation. So on the left is actually the convolution sort of spread out in matrix form, where you can see the stride is 1, and so it gets represented as this matrix where you're striding it by 1 in this form, and then this is the input vector, and this is zero padded because we have a zero padding 1. And so the output now is going to be equivalent to our input size, which is 1, 2, 3, 4. We had A, B, C, D inputs, and so we have the same number of inputs. Now, if we do the same thing, but we transpose that convolution instead, we're doing X, Y, Z, X, Y, Z, X, Y, Z. By the way, I think there's just an error in this thing here. It should be X, Y, Z, not X, Y, X. And so sorry about that. So that's, I think, what led to my confusion. But you can see you can now do this thing instead, and you transpose it, and the output now, instead of being a smaller or the same size as the input, we have a larger. We have that zero padding is no longer zero padding. It kind of expands it into an additional row. So, whoop, where am I going to be? I'll be here for now. So the idea is we can utilize this technique to upsample with learned weights. So the weights in this case, right, in the case of XYZ here, these would be weights in this particular stage. So this is just like the convolutional, the 2D convolution, except it's a transposed convolution, meaning we're doing it kind of the opposite. And again, I'm not going to go into depth on how to implement this because you also would have to do this with the gradient flow and all those things. So keep that in mind. But here on the bottom left is a good example, right? You have this input in the kernel, and now you're applying this, and you get this output that is larger than your input, and you've basically kind of upsampled this in a way. And you can kind of see that there is a relationship, right, between the input and the output in this case. And the our kernel is 0, 1, 2, 3, so both our input and our kernel have this sort of, you know, left to right, top to bottom growth, right? There's a gradient kind of pointing in this direction. And as you can see, our output has a similar gradient, right? Where the value in the top right corner is lesser than the bottom left and so on. But you can also kind of see that it's not like perfect. I mean, you have 4, 6, 12, 9. Y is 12 greater than 9 here. You can do the math and you can see why. But it's, you know, this is again, not a trivial type of operation. And so you really have to kind of be aware of when to use it. So when would you use it and why would you use it? You would use it in this context of a neural network and a bottleneck, right? So you would take your input, you would downsample, 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 and then you would upsample, upsample, upsample with transposed convolution. Now that's all good and nice, but the problem is you're manipulating this stuff and it's not necessarily rooted in the input data, right? So you can kind of take your image, scrunch it down into this sort of intermediate representation that has all this information about what objects are in the image, and then you expand that out into another image by upsampling. But the problem is now you've upsampled this image so now this feature representation knows which objects are in our scene, but it doesn't know where they are, right? It just knows that we have these objects in the scene, but it doesn't know necessarily and where it should put it. And so if you just transpose convolution it up to another image, you might sort of get these blobs that don't necessarily line up with the input. And so this idea of skip connections was introduced that sort of compensates for that, in that it now, instead of applying the transposed convolution operation to just your input from the previous stage, you also add to it an equivalent input activation from the other side of this bottleneck. So you can kind of imagine this being kind of like an hourglass, right? At each stage of an equivalent volume size, you sort of skip and you pass that into the transpose up. And so in that sense, each one of these stages has the opportunity to consider the spatial information of the data at that point on the previous sort of bottleneck sort of stage. And the implementation of this is really simple. There is no, you're just taking the activations and you're passing them to a different part in your network, which is why it's called a skip connection. And as you can kind of see here, right, say K is your kernel, the activation layer of a particular, the activations of a particular layer would just be the kernel convolved on the activations of your previous layer plus the activations of the equivalent layer on the other side. And this this architecture is called a U-net because it looks kind of like a U, and you can look this up, and U-net was like one of the first architectures that demonstrated this sort of semantic segmentation, which semantic segmentation allows you for each pixel in an image to determine what classification is that pixel. And this unit allowed you to sort of reconstruct that semantic segmentation from an input image directly. And so there's a lot of these sort of examples in the literature. The most interesting one recently is the mask RCNN, which kind of combines this idea with a region proposal network, which is a whole different thing. And if you're interested, by the way, in the computer vision stuff, I do recommend. There's a free, well, it's free. All the materials are free. Stanford's CS231N course is online. Something I've gone through. You get to implement stuff, and you get to learn about these kinds of problems much deeper than I will go into, because I mean, this is not a computer vision course, but it's a very, very powerful computer vision technique. So skip connections are really cool, and the context, I think, of what we're going to be doing is really important because of you can reconstruct spatial information. You basically create these networks that are able to output images, and in the context of game simulation, that seems like a pretty appealing capability. And you'll see a lot of these skip connections come up in a lot of different sort of generative models and things like that as well. So it's pretty important to know about. Cool. So it's a duplicate slide. Let's talk a little bit about a CNN before we kind of get into some interesting applications of these guys, which I'm pretty excited about. But let's just talk a little bit about VGG16. So VGG16 came out in 2014. This is after sort of AlexNet. It kind of pushed the state of the art a little bit further. After VGG16, we saw ResNets and the Inception architecture and so on that kind of pushed the state of the art past VGG16. So at this point, VGG16 is not like the state of the art, but it's still very much a popular model. It's used in the context of what's called transfer learning and fine-tuning, which we can talk about if you'd like. Please say something on the Discord, and I will keep that in mind. But let's take a look at just how this particular network, which only has 16 layers, sort of functionally works. And I think you can see all of the different things we talked about all in one place in the context of this particular network. So VGG16, as you can see, takes in an input. Its input is defined as 224 by 224 by 3, so it has 3 color channels and 224 square by square image. The first layer, as you can see, are 2 convolutional stages that are 3 by 3 in size. They have a stride of 1. The activation is a ReLU. And so after these 2 convolutions, the output size of the volume, because there's 64 of these filters, is going to be 224 by 224 by 64. So that means that we're using a stride of 1, but also there's a padding here that's not mentioned, because as you can see, the input size is equivalent to the output size. Then we employ a max pooling layer, which essentially is going to, with a stride of 2, which is essentially going to just, reduce our resolution by 2. And interestingly, they're applying a ReLU activation function here. I'm not sure if that's true or not. Often max pooling doesn't have a ReLU or an activation after it, but it doesn't like hurt in a way. If you think about ReLU, if you pass a ReLU to a ReLU, it should kind of be the same thing, right? It's just a input equals output if it's not negative. So applying a ReLU activation doesn't cost you much. It's more about just getting rid of the negative portion of the signal. So this is almost kind of unnecessary, but that's okay. Now we apply the 128 features of a 112 thing. The output is the same, and then we apply the max pooling. And you can kind of see this pattern, right? So we have 2 convolutional stages, then we shrink it. 2 convolutional stages, and each stage we multiply the number of features or the number of neurons by 2. So we go from 64 neurons to 512 neurons. And now at the end of this, we have 512 outputs that are 7 by 7, and then we unroll that into a fully connected layer. And you can see the size of that fully connected layer is quite large because it's 7 by 7 times 512, all right? That's quite a large thing. And then we shrink that down into a 4096, and then an additional 4096, which, by the way, 4096, you see this a lot in these sort of classification networks. That seems to be the sort of status quo feature vector representation of an image. 4096 works quite well. And then the output is 1,000 unit softmax. And what that means is that we have 1,000 classes in, I think this was trained on ImageNet, and ImageNet has 1,000 different classes. And so for each, now we kind of create a fully connected layer of 1,000 logits. Each one of those is going to give us a score, respectively, for a particular class, which we then use softmax as a loss function that we then use to backpropagate the error. And so this whole thing, in total, has 138 million parameters. So the memory of this is about half a gigabyte. And so you can think this doesn't sound like a lot today, both in terms of RAM or in hard drive space. But this was back in 2014, and being able to run something like this on a GPU with half a gigabyte of RAM, of VRAM, was probably I don't remember what 2014 looked like in terms of that, but I don't think it was super cheap to do. But yeah, this resulted in state-of-the-art top 1 and top 5 classification error in ImageNet, I believe, and it's still a very popular algorithm, a very popular network architecture to kind of start with and to play with. And maybe we'll talk about transfer learning and fine-tuning in a future lecture. But yeah, if you're interested in the paper, I'm covering it. So let me move myself over here, and you can kind of see. So check it out. It's linked in the slides. So yeah. One thing I wanted to talk about, and this is a little bit premature, I think, because GANs and unsupervised learning we'll talk about very soon in the course, so we're a bit ahead of ourselves. But I wanted to kind of share with you all this DC GAN, which was the first time a convolutional network was used in the context of a generative adversarial network. And you can kind of see this this deconvolutional, this transpose convolutional process working again, right? We have this idea, we start off with a latent space, which gets up-convolved into some kind of image. So these layers are actually trained in conjunction with this other network. So there are two networks that are sort of fighting each other in the context of a minimax game. So one is trying to create images to trick the other into thinking that they're real images. And this can be done with a convolutional neural network, which was more efficient substantially than the previous sort of fully connected approaches. And you can see some of the outputs of this image on the fashion, I forget what it's, the fashion data set. I forget the name of the data set, but it's basically a bunch of black and white images of like shoes and shirts and stuff. And so you can see the images that were generated by this look like real images, given the data set. So keep in mind this was done a while ago, and they didn't really push it with some of the bigger data sets and things like that. But I think most modern generative adversarial networks that are generating images are using a lot of sort of stuff from this sort of foundational paper. So you can see convolutions can be used in a lot of different things. In fact, convolution is very heavily utilized in reinforcement learning as well. For example, say I have a game that I'm playing, and I want to train a network, an AI, to kind of make the best decisions. We'll talk about reinforcement learning in the course as well. But I want to understand the scene. It's almost like I want to play the game as if I'm playing the game. I'm playing the game as like watching a screen, you know, or my TV or my video or whatever. And so what I can do is I can, just like we saw with VGG, in fact, I believe VGG is probably a pretty common network to use in this because it's a sort of like cheaper network versus some of the other ones. And we can use that to then create this representation that we can then utilize to make decisions and essentially what's called define a policy that the agent would use to hopefully maximize the potential score and to win the game, right? So yeah, there's a lot of convolution as a tool is seen almost across the entire landscape of machine learning, and so it's a very, very general kind of idea that I really encourage you all to sort of really dig into, because again, it just comes down to understanding this bit, right? Really understanding what's going on in this image, and you're good. And then hopefully understanding this bit, like the gradient is kind of important, and also just idea really that the gradient gets routed through the convolution in a more sort of distributed fashion than in the linear case, where in the linear case you have a very specific one-to-one connection between gradients and values and parameters, whereas here you have a more distributed thing. And the benefit of that is both in terms of scale and shift invariant. I forgot to mention scale, but scale is also a good one. It's not 100% invariant with scale, but it is to some degree. So yeah, that's it for this lecture. I have sort of a follow-up lecture that I'll also talk about with regards to frameworks. So again, in the context of frameworks, I'll just save it for the next lecture because I'm going to record that now. But yeah, convolution, it's cool, and it's not as scary as it sounds. I know that I personally spent probably like half a year studying machine learning fundamentals before I had sort of the courage to go and dive into convolution. When I did, I realized it's actually not that hard. It's just a very simplified Just a manipulation on the same ideas that we've seen so far, but it has some significant benefits in terms of computation, in terms of just properties that it has that look like all of this you can theoretically do with fully connected layers. But it's intractable. The computation would be hard. Getting the networks to do what you want will be hard. That's sort of where I think machine learning is a little bit different than traditional software architecture and traditional software development, is that it's more like landscaping, right? You kind of define your landscape and the flow, and you set everything up, and then you hit the go button, and you hope that the plants grow where they're supposed to grow, and that the people walk on the path where they're supposed to walk. It's almost like planning, and then but in reality, right, things don't happen exactly the way you want them to because of all these dynamics, and so then you have to kind of mess around. And so in a way, convolutional neural networks, like fully connected networks, are just a tool in the tool belt to sort of build these landscapes. Cool. All right, I'll see you next lecture.